Okay, today let's talk about some continuity, section 5.2. Now, last time we were talking about limits existing, and this time we're going to be talking about continuity, and the two are married together. But remember that a function can have a limit at c even if it isn't continuous. For example, we just have a simple function, there's c, and then we have a curve. Then it's possible that when you stick in c that the function is actually undefined. Right? There could be a hole in the graph. Or maybe it is even defined, but it has a value that's not what it's supposed to be according to the rest of the graph, right? So this example would still have a limit as x approaches c, right? And in fact that limit would be somewhere over here, right, at L, but the function itself is not continuous. So it can have a limit even if it isn't continuous. And that's a classic example, the holy functions, the church functions. Okay, so let's define now. We'll define continuity as follows, that if we'll let f be a function that goes from some domain into R and let c be an element of the domain, we will say that f is continuous at c. F is continuous at c if for every epsilon greater than 0, there, let's erase that, make it nicer. If for every epsilon greater than 0, there is a delta greater than 0, such that f of x minus f of c is less than epsilon when x minus c is less than delta. Oh, and x is in D, of course, has to be part of the domain. Okay, so the only real difference from the previous definition of limit existing is that now we're not going towards some generic L as a limit, but we're actually going to the functional value, the f of c, the actual output of the function. And we are also including, it's not a deleted neighborhood anymore, because we're also including that the value of c has to go to the correct place. So it's not a deleted neighborhood anymore, it's now actually the value that you stick in c goes to f of c. It doesn't freak out and go to some other point. Okay, so this would be continuous at a particular point. So then we'll say that f is continuous on some set S if, essentially, f is continuous at each x in S. So now it makes sense, or that's the definition of what it means to be continuous on a set. And then we'll just generally say that f is a continuous function if f is continuous at each x in the domain, so the entire domain. So polynomials we saw, polynomials for example, are continuous functions because they are continuous at every single point in their domain, which is all the real numbers. Okay, so note carefully, the limit definition required that c be an accumulation point, but this is not needed for continuity. Continuity did not require the accumulation point, so isolated points work. So in fact, if x were an isolated point, then there's a neighborhood around it with only x in it. Remember, an isolated point means it's kind of lying on an axis here. And if x is isolated, then that means that there are no points around it that are included inside of the domain. So then what would happen? Well, regardless of any epsilon, whatever epsilon you're given, we would have what? Well, we'd be able to make a little window around x since it's isolated so that the only point in there would be x, and then so we would have that f of x minus the actual f of c, since that's the only point in there, would actually be literally equal to 0, because that's the only point that would be inside of that particular little neighborhood for any x in that neighborhood. Right, so neighborhoods are connected with the epsilon-delta and they're connected with the sequences. Right, all of these are different representations of continuity and limits and just different definitions and ways of looking at things. Okay, so that doesn't matter there. And now here's the big theorem of this particular unit, is that if f is a function going from D to R and C is any point in the domain, then the following statements are equivalent. Number one, f is continuous at C. Okay, remember that this would be our epsilon-delta definition. that I put on the previous page, a couple pages ago. Number 2, if xn is a sequence and xn goes towards c, then what has to happen? Well, then we would have to have that the limit as n goes towards infinity of the f xn's, well, they're going to have to go to f of c. So there's the epsilon delta in number 1, then there's the sequence type definition or sequence equivalency characterization in step 2, and then 3 we have more of a topological type statement, which would be for every neighborhood v of f of c, so this would be on the y-axis, there exists a neighborhood u of c on the x-axis such that f of the u on the x-axis intersected with the domain, so only domain relevant points, would have to be a subset of v. And if in addition to these, right, all of these are equivalent, they all mean the same thing, but if a function is continuous and c happens to be an accumulation point, then we know that it has a limit at c from 5.1, and that the limit as x approaches c of f of x must be f of c. And that's our standard, I circled here, calculus, because this is how we defined continuity in calculus, is that the limit had to exist, the functional value had to exist, and the limit as x approaches c of f of x was the functional value. So that's from lower division calculus. That's how you've always defined it. So nothing different going on here. Now, so far it's been a bunch of words, so let's put some pictures to this so we can better understand. Okay, so what's the epsilon delta definition effectively doing? Well, it says for all epsilon greater than 0, for all epsilon greater than 0, we're going to make a little window around f of c. So there's f of c plus epsilon, f of c minus epsilon. For all epsilon greater than 0, there exists a delta greater than 0 that's going to create a window around the c on the x-axis. So there's a c plus delta and there's a c minus delta. And what is this going to cause? Well, c minus delta, well, let's go over here first. F of x minus e comes over here. F of x plus epsilon somewhere over here. And what we're seeing is that the c minus delta, c plus delta, this little window, all of the values that are given, or every time we take a function, evaluate the function at a point on this interval, it's always going to fall within the epsilon window on the y-axis. So that's for all epsilon greater than 0, there exists a delta, so that whenever we are within delta of c, we get that the functional value is close to f of c, being close to f of c. So things close to c get sent close to f of c, and that's really what the epsilon delta is saying. On the other hand, what's the sequence definition saying? Well, the sequence definition is saying that if there is a sequence that heads towards c, for example, there's maybe an x1, and there's maybe an x2, and then maybe there's an xn, and if you have some kind of sequence that's heading towards c, then if you take the functional values, so here would be f of x1, and then here would be f of x2, and then dot 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 dot, maybe eventually we get up here to f of xn. And notice that if that sequence on the x-axis was going towards c, then the functional values of the sequence must head towards f of c. And based on what we've done in the entire last chapter, chapter 4, we know that the definition of the sequence is an epsilon n definition, and so sometimes it'll be easier to work with sequences, and sometimes it's easier to work with epsilon deltas and just use different windows. And finally, the topological definition, the neighborhood definition, was if you have a neighborhood v around f of c, so maybe you have a window that looks like this. It doesn't have to be equidistant on either side, but just has to be any neighborhood. And if we take this and come over to our x-axis, so take those as our y's, come down to the x-axis, then there has to exist a neighborhood u that you can place around c such that every single value in U, technically U intersect D, but in U, gets sent through the function, via the function, into values that fall within the V neighborhood. So all of these definitions are equivalent, and depending on context, different ones will be easier to use in different contexts. So here's a cool example. We'll refer to this example later, so keep very good note of it. Let f of x equal the function x sine 1 over x for x not equal to 0, and then we will define it to be evaluated as 0 when x does equal 0. Again, note that the function itself is not technically defined at 0 with the x sine 1 over x, so this is filling in the hole that's missing. But it turns out this is an appropriate fill-in of the hole because the function will actually still be continuous at 0. We're going to show that it's continuous at 0 right now. So claim f of x is continuous at 0, and for this proof let's do a epsilon-delta argument. Okay, so how do we start off an epsilon-delta proof? Given epsilon greater than 0, let's choose delta to be equal to epsilon. If we now assume that x minus 0, notice that's x, is less than delta, then what do we get to see? Well, notice that f of x minus f of 0 would be equal to x sine 1 over x minus 0, in almost all cases, right, except for 0 itself. This is equal to x sine 1 over x, and because sine is bounded by 1, right, sine never exceeds 1, that means an upper bound on x sine 1 over x would just be x. Then from our assumption, we said that we were going to assume that x was less than delta, and we actually chose our delta to be equal to epsilon. So therefore, f is continuous at 0. Now, keep track of this one again. This is continuity at 0, and I will make an argument later on in this lecture where we end up concluding that x sine 1 over x is actually continuous everywhere, because everywhere except for 0 can be argued to be continuous fairly easily, but it'll be reserved for later. Okay, here's a useful characterization. Let f be a function from a domain D to R, and let C be any element of the domain. Then f is discontinuous at C if and only if. Okay, well, remember that our big theorem says that f is continuous at C if and only if there's this sequence part, or sequence characterization, if and only if there's a neighborhood characterization. So what we're going to notice as a useful characterization over here is that it will be discontinuous, a function will be discontinuous at a point C, if and only if there is a sequence that you can find in D such that xn, the sequence, converges to C, so we have a sequence that's heading towards that particular x value on the x-axis, but f of xn does not converge to f of C. Okay, so in other words, we're going to see one way that you can show that a function is discontinuous is if you can simply just pick up a sequence that heads towards the x value that you want, but that you can show that the functional values, the f of xn's, do not go towards f of C. They go towards something else. And again, that's just negations, effectively, of our big theorem statements. Okay, so here is an example. Let f of x equal 1 over x squared on the domain of everything but 0, negative infinity to 0, union 0 to infinity. Okay, first of all, notice that the limit as x approaches C of 1 over x squared is equal to, oh, forgot to put it there, 1 over C squared. Right, certainly equal to 1 over C squared. And the only point that causes any kind of problem would be 0, right? 0 is a dangerous point because 0 is not inside of the domain. But could we make it be a good point? Could we fill this one in kind of how we did with the sine of x function over here? With this x sine 1 over x, there was a problem at 0, but we simply filled it in. We filled it in with the appropriate value and made the function continuous at 0. But this function now, it looks like 0 is dangerous, it's not in the domain. Can we define it somehow to make it continuous at 0? Well, let's try. Well, suppose that we define f of 0 to be any number, really, to be k. So f of 0 equals k. So f of 0 equals k. Let me be a little bit clearer with that. f0 equals k. Okay, this turns out to be a problem because notice what is true about the sequence 1 over n. Well, 1 over n, the sequence would be 1, 1/2, 1/3, 1/4, 1/5. So that function, or sorry, that sequence heads towards 0. But what's true about the f of 1 over n sequence? Well, notice if you stick 1 over n into the f function, you end up getting n squared. And what's true about the n squared function? Well, that would be n squared function, sorry. N squared sequence is that it would be 1, 4, 9, 16, 25. In other words, it would go towards infinity. So what is that? So what happens? So that means f of 1 over n doesn't even converge. It actually diverges to positive infinity. So in our case here, f simply cannot ever be defined. Cannot. So f simply cannot be made continuous. Well, it'll be defined, of course, but it can't be made continuous at 0. No matter what we tried to define it to be, if we tried to set it up as some value k, then our 1 over n sequence would head towards 0, so we would have to have that the f of 1 over n's would have to go to k, but we can see that the f of 1 over n's don't converge to anything. They always extend or diverge off to positive infinity. So 1 over x squared is a different kind of discontinuity than x times sine 1 over x. X sine 1 over x was removable. We could fill it in. But 1 over x squared has a necessary discontinuity. Okay, here's a handful of cool functions out here now. Dirichlet function. The Dirichlet function is defined to be equal to 1 if x is a rational number, and it's defined to be 0 if x is an irrational number. So what would this function look like? Well, it's a pretty crazy function. It's defined on all of the real numbers, and every time you use a rational number, 1/2, 1/3, 7, the function is always equal to 1. But every time you stick in an irrational number, like radical 2 or pi or e or anything like this, the function is always, on those points, equal to 0. From our previous units, we know that the rationals and the irrationals are both dense in R, so that means that this function is jumping up and down and up and down and up and down between 1 and 0 all the time. So we can make a claim here. It turns out that f of x is actually discontinuous at every single c in the real numbers. So I am going to make an argument here about using the neighborhoods, but every argument that you make could be transferable into an epsilon-delta argument or a sequence argument. So I'd encourage you to pause here for a second, try to recreate or try to create an argument in either a neighborhood form or a sequence form or an epsilon-delta form. But I will approach this with a neighborhood type argument, just an example to model it. So we have to show that f of x is discontinuous at every single point, so let's let c be any old real number. Okay, notice that any neighborhood of c contains both rational numbers and irrational numbers. Right? Because rational numbers and irrational numbers are both dense in R. So if you take any open neighborhood, you'll have some rational numbers and some irrational numbers. But what does that imply? Well, so there will always be points that are sent via the function to 1 and other points that are sent to 0 on any neighborhood of C. So notice that means that no matter what, if we remember, it's supposed to be, the neighborhood definition said that for any neighborhood we put around that supposed limiting value, that functional value, we are supposed to be able to find some kind of neighborhood around the domain value that always falls within that interval, or inside of that neighborhood. But that won't happen here, because no matter what, we always flip out between 0 and 1. We don't get really close to anything. Sometimes we're 0, sometimes we're 1. We're all over the place. So that allows us to conclude here that f of x is discontinuous at C. We never get really close to anything along the y-axis. Okay, so that's an example of a function that is defined on the entire domain. It's defined on all of R, but it's actually continuous nowhere. There is nowhere that it is continuous. Okay, let's modify that argument into what we call sometimes the modified Dirichlet function. This function, f of x, is equal to x if x is a rational number, and it's equal to 0 if x is an irrational number. So pause for a second, see if you can sketch a quick graph of this if you want to on your own. I'm going to sketch it down here, but you should pause and see if you can draw it on your own and think about it. It's kind of a funny looking graph, because this time the function is again with rational numbers, right? So rational numbers are dense, so that means it's essentially going to be f of x equals x most of the time. So it'll look kind of like this, but with infinitely many holes, right? Because there's always irrational numbers floating around also. And for those irrational numbers, the functional value comes out to be 0, so that means it's always going to be here on the x-axis. And so it looks like that. So it's another jumpy function, right? It keeps jumping up and down between x and 0, x and 0, x and 0. So 1 and 0 over here, and 7 and 0 over here, and 1/2 and 0 here. But what's interesting about this function is that unlike the standard Dirichlet function, which was continuous nowhere, this function is actually continuous at one single point, namely 0. Don't believe me? Let's prove it. Last time we did a neighborhood argument on the last slide, so this time I'm going to choose to do an epsilon-delta argument to model this type of argument. So again, pause the video if you wish to try to do an argument on your own, either epsilon-delta, neighborhood, or sequence. But if I'm approaching it by an epsilon-delta argument, my proof would have to begin with, let epsilon greater than 0 be given. We're going to choose delta equal to, and you have to do a little discussion on the side, but it turns out that this is really, since it's f of x equals x effectively, the epsilon is going to be a good choice for delta. We'll just choose delta to be equal to epsilon. So now if we simply assume that x minus 0, notice that that's just absolute value of x, if we assume that this is less than delta, then what do we get to see? Well, notice that f of x minus 0 would be equal to f of x, which is less than or equal to x, because it's either x itself or it's 0, and 0 is less than or equal to x, absolute value. But by our assumption, x is less than delta, and I chose delta to be equal to epsilon. Yay! So we get to see that f is continuous at 0. We have a nice epsilon delta argument, and we have a nice neighborhood argument on the other function. Okay, now for our last example, let's look at the Thomé function. Let f of x equal 1 over n if x equals m over n for rational numbers, as long as that fraction is reduced to lowest terms, and we'll let it be 0 if x is an irrational number. Okay, so this one's a really sneaky function. So f of pi, right? Pi is irrational. F of pi equals 0. F of rad 2 equals 0. F of any number, f of e, any irrational number is always going to be 0. But then what are f of these other rational numbers? Well, f of 1/2 would simply be 1/2, because 1/2 is a fraction that's already been reduced to lowest terms. F of 1/5 would just be 1/5, because 1/5 is a fraction that's already been reduced to lowest terms. F of 2/3. Now we don't want this to get too big, so what we're going to do with 2/3 is, notice the definition says that if we're a rational number reduced into lowest terms, then we will let the functional value be 1 over that same denominator. So f of 2/3 is actually equal to 1/3. F of something like 8/10. Well, 8/10 is not reduced. So 8/10 we'd have to first reduce that into 4/5. So I'm not changing anything by calling it 4/5. But f of 4/5 would be 1/5, because again, we don't take the numerator that was actually the numerator of the fraction. We only take the denominator and make 1 over, make the unitary fraction out of that denominator. Wow, so this function is really cute. It's going to look something like this. You get a lot of zeros again, mostly zeros along every irrational number, so zeros down here. When we stick in a number like 1/2, we get 1/2, so that might look something like here. 1/3 and 2/3 both yield 1/3. Right? F of 2/3 is 1/3, f of 1/3 is also 1/3. So wherever 1/3 is and wherever 2/3 are both going to spit out a value that is 1/3. Getting the pattern now? What's going to happen to f of 1/4 and f of 3/4? Well, f of 1/4 is going to be 1/4, and f of 3/4 is going to be 1/4. F of 2/4 would actually be this value right here, because remember 2/4 reduces to 1/2. So that would look something like here. There's the 1/4 and the 1/4 occurring at 1/4 and 3/4. Okay, at the fifths we saw f of 1/5 and we saw f of 4/5, so it's actually going to have a 1/5 and a 2/5 and a 3/5 and a 4/5, all giving you these values. And so we end up getting a very fancy picture here, but the picture is actually going to have some continuous points. So where is the function continuous? Well, the argument for this has been wonderfully covered by Gladys during one of her talks. So Gladys did an epsilon-delta argument in one of her talks, and our textbook does a pretty elegant sequence approach to this fact. I think we might reserve this one for class if we need to express it in other details, but I'd encourage you to read the book on your own for this one, and we'll go through extra details if we need to in class or through office hours. But both of the arguments that are given, either the epsilon-delta argument in Gladys's talk or the sequence argument in the textbook, are both pretty clear, and they're very nice arguments. But it's a really weird function to look at, right? Okay, so let's look at a basic theorem now that's going to apply all of these facts and make it easier to establish continuity of different functions that are composed of other functions. Okay, f and g are continuous. I'll do a sequence definition proof on this one because we've already modeled an epsilon-delta argument here. We have modeled a neighborhood argument. So let's do a sequence argument for one of these facts. But if f and g are continuous at c, then it turns out that f plus g is continuous at c, f multiplied by g is continuous at c, and as long as g of c is never equal to 0, we also get that f over g is continuous at c. Again, as long as g of c is never equal to 0, not allowing us to get a denominator of 0. So let's do a short little proof, or sequence proof, of, let's do the sum of the sum fact. So, of 1. Okay. So, sequence definition would require us to say, let f, no, not f, sorry, we have to let there be a sequence, so let xn be a sequence that converges to c. Notice that the limit of f plus g evaluated at xn is going to be equal to the limit of f xn plus g xn, and that's just equal to the limit of f xn plus the limit of g xn. And because the other sequences are continuous at c, that means that since xn is going towards c, the limit of f of xn is just f of c, and the limit of g of xn is just g of c. So we end up getting f plus g of c. Right? That's a sequence argument. So all of the groundwork that we laid, all the hard work that you did in chapter 4, learning about sequences, can simplify proofs in the continuity stages because we can use the sequence characterization of continuity. We have epsilon-delta, we have sequences, and then we have those topological neighborhood arguments that would be useful if we moved into topology sometime in the future. Okay, here's another theorem. Let's suppose that over here we did addition, multiplication, division. Let's talk about composition, because that's a special function operation that is useful in calculus. So suppose that we have f, which is a function going from d to r, and that g is a function that goes from e to r, and we know that f of d is a subset of e. So everything that goes into f goes to d, goes through d and gets into r, but then we also know that the image of d is a subset of e. So after we do f, we can then do g to things. Well, it turns out that if f is continuous at c, and that g is continuous at f of c, whatever that functional value is, then the composition of those two functions will be continuous at c. Okay, so as a picture here, I'm going to do, let's do a, what should we do on this one? Let's do a topological argument, neighborhood argument on this. I was going to do epsilon-delta, but I think topology might be easier here. So the picture looks something like this. Well, technically it's R, but let's just say here's a picture of a point C in the initial domain. So this would be like a picture of D, essentially. Then it gets mapped over by F into a new set, E, still a subset of the reals, and f of c itself got stuck maybe, let's say, like right there. And then there's a g function which is going to take that and move it over into another space, and that other space is going to have the g composed f of c. And we're simply saying that we'll be able to find a continuous, or that this function would be, as long as you're continuous at c, f is continuous at c, and if g is continuous at f of c, then the composition graph, or the composition function, will be continuous at c also. Okay, so we're definitely going to have to make a neighborhood argument here. So that was for any neighborhood in the range space. So as I go over into the next page and start doing the proof, I'm going to have to refer to neighborhoods. So let's be consistent here. Let's set up some neighborhoods right now. I'll put a neighborhood around this one. Remember, neighborhood's just an open set that contains g of f of c. And we'll call that w in the furthest space. And then over here we'll have a little neighborhood around f of c, and we'll be referring to that one as v. And then we'll have a neighborhood around c, which we'll call u. The u and the v in particular are consistent with our definition. If you go back to that big theorem at the beginning there, the three things that are equivalent, we said that v would have been a neighborhood on the range space around f of c, and then u would have been a neighborhood around C in the domain. We just have to introduce a third one now because G composed f of C is going to be a third space. Okay, so let's begin our argument. Let W be a neighborhood of G composed f of C. And we're hoping that given a neighborhood around G of f of C, we can find a neighborhood around C so that every point that is sent via f in that neighborhood around C will be sent into this W neighborhood of G composed f of C. Well, since G is continuous at f of C, there has to be a neighborhood V of f of C with G of V intersected E being a subset of W. So here we're calling upon the continuity of G at f of C. So G is continuous at f of C means there has to be a neighborhood that causes this to happen. Okay, but then the next step, we also knew that f was continuous. And where was f continuous? Well, f is continuous at, f was continuous at C. Since f is continuous at C, we know there is a neighborhood U of C with f of U intersected with the domain being a subset of V. So just like in the picture now, we have this U that gets sent really close to f of C, in fact within V of, or inside of this V neighborhood, and then because of G's continuity we know that everything in V is sent really close to G of f of C. So we get to conclude that since, because f of D was a subset of E, we now get that f of U intersect D is a subset of V intersect E. Everything in D was sent to E. F of D was a subset of E. So G of f of U intersect D, we take everything from F, or everything from U intersect D, we send it under the F map. It gets sent into V, right, that little neighborhood around f of C. But then everything that's in V, when we apply G to it, gets sent into W. So this is just a subset of W. And as needed then, F composed G is continuous. G composed F. Yes, we gotta go G composed F because we did F first. So G composed F is continuous at C. So that's an illustration of another neighborhood type argument, a topological type argument. Great. Okay, so remember I promised you would refer back to that example from the beginning. Well, let G of x equal sine of x, and let h of x equal 1 over x. Then for x not equal to 0, and assuming, oh yeah, I had to make a note of this, that we have to, I'm assuming that sine of x is continuous. It is, but we didn't really argue that, so we are assuming sine of x is continuous. But for all x is not equal to 0, then both g of x and h of x are continuous. So sine of 1 over x, which is the composition of g and h, is continuous. Furthermore, products are continuous. So x multiplied by sine 1 over x is continuous for x's that are not equal to 0. But remember, in our very first example, we showed that also x sine 1 over x is continuous at 0 if, in addition, we define the function to take the value the value of 0 at 0. So the big conclusion now is that the function f of x, defined by x sine 1 over x for x not equal to 0, and also chosen to be 0 if x is equal to 0, is continuous on all of R. It's continuous absolutely everywhere in the real numbers. Okay, so another topology connection here that is a good one to keep mind of is that a function is continuous if and only if the inverse image of an open set is open. So if G is an open set and we take the inverse image of an open set and that's open, that's all you need to have a function that's continuous. So this is the standard definition of continuity in a topology class where you don't have any kind of measurement, you don't have a metric necessarily. So consider f of x equals x if x is less than or equal to 2, and 4 if x is bigger than 2. Quick little sketch over here. So go to the value of 2 and let the function be the line slope 1 through the origin up until 2, and then we'll let it be constant function 4 for everything beyond there. So there's the function. Notice the function is just visually not continuous. Consider the set G to be the interval from 1 to 3. So let G be the interval from 1 to 3. So that means G is supposed to be inverse image of G, so we have to be on this axis. So there's 1, there's 2, and there's 3. And also notice that 1, 3 is an open set, right? 1, 3 is certainly open. Well, what is the inverse image of G? Well, the inverse image of G, what things do you stick into F that get you between 1 and 3 on the y-axis? Answer? Well, starting at 1, you start at 1 for sure, so there's going to be 1. And since it's an open interval 1, I have to use an open interval here, right? I can't get all the way down to 1, but I can get everything up to, but not quite including 1. But on the high end, notice that everything that's included up to 3 would actually be up to the closed interval of 2, or the closed point of 2. Because 2 is sent to 2, which is inside of the interval from 1 to 3, but then nothing beyond 2 is sent to between 1 and 3, because once you go beyond 2 over to here, for example, those functional values get warped up to 4. They jumped up to 4. So the inverse image of this open set is equal to this non-open set, and therefore this function is not continuous. And we didn't need to talk about any kind of measurement or metric. Okay, your homework is to try problems 1 and 2, which are true-false problems, and then 10, 11, 13, and 16, which are some proof problems that are used in future units. And really look at that Thomé functions argument inside of the textbook, because we might review that one again in class when we meet next Tuesday.